Welcome to Smith's Interconnect 360 Connectivity Podcast. Join our experts as they explore high-end and cutting-edge topics that shape and influence the connectivity world. Enjoy this week's episode.
Welcome to Smith's Interconnect 360 Connectivity Podcast, the podcast that explores connectivity trends and applications in today's manufacturing sector. I'm Tim Wooden, the Market Development Director for the Semi-Test Business Unit, and today I'm with a friend and coworker, Joshua Daniel. He actually goes by Josh, Product Line Manager for the reliability test portion of the semiconductor test BU. Today we'll be discussing the challenges and the requirements for testing advanced semiconductors running at and up to 224 gigabit per second PAM-4, and really focused on AI and hyperscale applications and how we got here today. So let's get started.
Yeah, thanks for the intro, Tim. Happy to be here with you and shed some light on this next generation technology. I think that to start it off, we want to share some background on market status. So we know that the big players like NVIDIA, Google, Microsoft, and AMD are all investing heavily in ASICs, specialized for segments like AI, high power computing, data centers, consumer, memory, so on and so forth. So based on what you've seen so far, how pivotal are the critical advancements in the development of the technologies to ensure the success of these product releases?
Yeah, we in the semiconductor industry has always just had a drive and ambition for more, faster, more efficient computing power. And as we dive deeper and deeper into these AI hyperscale applications, the demand for higher memory capacity and faster data rates is paramount to the success of these applications rolling out. Without these critical advancements and the memory technology specifically, the performance of these specialized ASICs would be severely limited. It's like having a race car, and you have to pedal that race car with your feet. I mean,
Fred Flintstone style, huh?
Absolutely. And to keep up with these increasing bandwidth demands of the applications, the semiconductor devices need to communicate at data rates, at least chip to chip, in what today is 100 gigabits per second. We have some customers 112 gigabits per second, but the near future is 224 gigabits per second, and that is the digital data rate, but running a fundamental Nyquist frequency of 56 gigahertz. Just as they start to run multiple GPUs in parallel to create these hyper-thread nodes and these data center clusters where they can link up to 256 nodes, which are the GPU and app-specific accelerators running in parallel. We are on the edge of the greatest technology shift since the emergence of the internet. I think that is as true of a statement as I've heard over the last year and a half. The impact and the value of generative AI is really difficult to measure, since AI has the potential to fundamentally change industries from automotive to scientific research and even medical treatment. What's happening today is really, really early on, and the results that they're getting are mind-blowing. So it's exciting.
Yeah, it's incredibly powerful. I mean, some of the things we're seeing in the medical fields where AI is able to diagnose some of these symptoms that would take years and years and years for a traditional medical doctor to do is very impressive. So obviously things are running faster, they're going to be running hotter, they're going to need to be smarter. So when we look at the qualification process of these new devices, the test hardware needs to be much more capable than it ever was before to handle that next step in the generation of the technology. So what are some of the biggest hurdles and for these interconnects to get over when providing a solution?
I think what is most important is really quite simple. It's moving the most amount of data in the shortest amount of time, with the least amount of latency. And the transition to 224 gigabit PAM-4 or PAM-6 or PAM-8 or QAM-16 transmission lines are really paramount to, again, the success of these applications rolling out. Uh, because as data centers are power hungry, uh, the different types of signaling will allow for these to be more power efficient. And this power integrity needs to be optimized through the electromechanical interconnect. And then coming back into the power conversation is each one of these new devices keeps pushing the envelope of their thermal design power. I think the next device that we are working on internally is expected to run at 1.4 kilowatts. We don't really see that slowing down. What we do see is that these larger devices, or these devices, are getting larger. So although the power is increasing, the power density in some cases is actually being reduced as the devices are getting so much larger than the previous generation.
Yeah, from a reliability side, 5 years ago, 10, 12, 20 watts was on the cutting edge. And so now when we're working with applications constantly in the 500 to 800 watt range, just goes to show you the power intensity of these devices.
What do you guys do when you get one of those requests from a customer that comes in from a reliability perspective? If you were so much of the business has been focused on that low power, and then you get a request for 500 watts, 600 watts. What do you guys do?
We went through about a year long learning cycle to get over the hump of understanding a couple of different things, right? First off, the mechanical fixturing of such a large device, with warpage and heat, things are going to get a little malleable in there. So applying proper force without damaging the device is a big, big thing. And once you've got everything seated in a socket, the next step is how do you get all the heat out? And so we've gone through several iterations of cutting edge heat sinking uh, solutions and wound up somewhere where we can actually flush water through the system and instantly cool these devices running at, like I said, 500, 800 watts. So by no means was it easy. It was fun most of the time, and we found success on the other end. So it's just keeping your head down and knowing that you can find a solution.
So, back to the original question of how we really do achieve this, to get to this next level of signaling and high speed, our customers really are uh, more and more using SerDes into their designs. And the reason they're using SerDes is just for the high speed data transmission. This is so that they can be achieved without requiring excessive number of interconnects. The SerDes is serial deserialized, so they could send multiple lines of code on the same line, and then serialized, and then deserialize it to uh, reduce the size of the transmission. And this also reduces power consumption and the cost associated with the interconnect design, as the IP developed around SerDes is pretty great and substantial. And kind of goes to show why early on in the what we coined AI, or um, the high performance compute segment, that FPGAs were so important, that the FPGAs really did a lot of the high speed uh, signaling. And the reason was that they could be programmed to do multiple tasks in conjunction with an off-the-shelf GPU or a off-the-shelf CPU. But now we're starting to see more of our customers design their own ASICs to accommodate specific tasks and enabling faster, more reliable communication between devices, servers, networks, and ultimately out on the edge, whether that's your TV or your handset or uh, even your Ray-Bans with uh, camera embedded. So during the design phase, we really focus on a few key areas to ensure we have an out-of-the-box solution. Signal integrity being number one. The impact of channel losses, reflections, crosstalk on the high-speed signal integrity is why we need accurate modeling and simulation of the channel prior to manufacturing the product. Equalization techniques to compensate for channel impairments in the system is important on our side, whether that's designing a cavity and a spring probe that sits in that cavity, uh, and then running a simulation, evaluating the impact of the cavity design, then going back and updating that cavity to make sure that it's not the weakest leak in the system, as that really has the potential to be the critical failure. And most of all, and I think we're seeing more of a transition to customers talking about this. Customers did not talk about this for up until, I don't know, early this last year, but power integrity. And power integrity is not just through the electromechanical interconnect, but it is absolutely from the system board all the way up to the DUT and back down through the system board. So uh, power integrity is being looked at holistically, and any neglect of power delivery will have a great impact on the performance of the SerDes, and will definitely result in critical failures. The challenges in neglecting power integrity are voltage drops across the system, as we have multiple pulse amplitude modulation today. We are sending multiple bits of data on each clock cycle at different voltages. So any drop in uh, voltage, or if the accurate voltage is not seen during the clock cycle, it'll come back with a bit error rate, and this definitely can impact a pass-fail criteria in back-end tests. So we have immense challenges related to power integrity, and they're not just on our side, but it's the PCB designers making sure that they're decoupling on the PCB. You see a lot of the ICs that customers are designing have chip capacitors on the substrate and on the backside of the device itself. And a lot of the challenges we're facing today. So the final key to that would just be running a full system signal integrity solution, and that is something that more customers are doing in-house. They're getting full electrical, whether it's a SPICE model or HFSS from us, their PCB vendor, and then a lot of the design work they have done internally. Then they'll run a full system uh, simulation for PDN and signal integrity.
You made a good point about PCB concerns when you're talking about power integrity, especially when you're on the smaller devices and you think you're only running half a watt on this 4x4 device, and next thing you know, everything's getting extremely hot. So we've had to delve into more and more backup heat sinking from the bottom side of the board, simply because there are components there and they have limited temperature restraints. So we are seeing that more and more these days. But I guess from a system level test side, that's where the DaVinci coaxial test socket comes into play, right? It's really the forefront of system level socket technology. So how has the DaVinci been with these high performance devices under such extreme tests?
I think that as we kind of talked about, what we didn't go into at the opening here was how our relationship began. Smith's Interconnect acquired Plastronics. Josh is a member of that Plastronics group, which was focused on the reliability burn-in test portion of our business. And the Smiths Interconnect, prior to the acquisition of the Plastronics business, was really focused on high-speed test, back-end tests, not the reliability side. And there is a lot of differences in between that, but as Josh and I have been working in lockstep over the last year and a half since acquisition, that a lot of it is blurring the lines. And we talk about our DaVinci test socket, which really has been a game changer in the market. We were incredibly proud to be the market leaders in the high performance test socket market. The secret to our DaVinci product in particular lies in the socket's ability to isolate the high-speed signals, the single-ended signals in particular, from crosstalk, as these devices are laid out in a way that have many more single-ended signaling, where we could have in a 5,000 pin device, we could have 2,000 to 2,600 single-ended signals in a very small footprint that we need to make sure and isolate the signal from the signal next to it so that it doesn't have any impact on the signal integrity. And it's just due to the patented coaxial structure, which ensures that the highest signal integrity, and it really limits the losses when testing semiconductor devices. And the neat part about the DaVinci product is that each signal pin is a fully assembled signal. So these are field repairable products that can be replaced like any other spring pin. These are made for mass production, and they've really just been designed to go into today's HVM manufacturing facilities and work. So not only does our DaVinci product continue to outpace the previous generation of the DaVinci product, today we are testing at 112 gigabit per second PAM-4, which is some of the fastest and most stringent GPU, APU, TPU applications on the market today. But the DaVinci test socket was uniquely designed to overcome these challenges of increased bandwidth for integrated circuit testing. And the way that we continue to do that is through our lessons learned on each product, but now working with the reliability team to understanding a little bit more of what reliability engineers are looking at, system level teams, the ATE teams, and trying to just capture as much real world conversation and data from how our end customers are using the products. And we've kind of surmised these 4 critical path requirements to ensure that the test socket does not become a bottleneck in achieving the next generation bandwidth. And so far, it's worked. The first to that is IR drop. We really have for quite some time focused on the power signal probes and how they're designed. The cavity is designed for optimal power impedance. Our crosstalk isolation is unmatched in the market. We have fully isolated signal probes in a coaxial structure, which provides shielding to the high-speed IOs. Our and then PSIJ, which is the power supply induced noise. This is complete socket model provided to the customer for simulation, for psi wave simulation, again, just focused on power delivery. And then signal degradation, socket impedance matching, and using our HFSS simulation to ensure that we are achieving the optimal signal. We have margin built in to allow for loss in other parts of the system and matching system impedances where it was pretty standard that 50 ohm was what everybody designed to, and I think over the last 5 years that has really not been so rigid any longer. I mean, I think we're designing a lot for 43, 46, 50 for single-ended, and 85, 86, 100 for differential.
So let me touch on something you said back there. The field repair capability of these sockets, because it is fully isolated signal probes, so in the DaVinci. So do you guys send someone out to do the repair, or is that something that the customer is able to do on site in the lab?
So, I think it's both, right? I think there is maintenance schedules done at production floors, and where this would be done normally as part of a preventative maintenance program. But it is also happens in labs or at a customer's cube. And it may be a case where the production floor has experience in replacing pins because they are part of preventative maintenance. But when it ends up with an engineer in their lab or in their cube, I'm not knocking any engineers that are listening to this, but replacing a single spring probe can be
It
a
could ruin your whole
monumental.
day.
It could be a monumental task for such a tiny part, right? Like it absolutely. So in those cases, we would have somebody come over if asked, or we'd pick it up, just double check everything else, and do it at somewhere at a local facility. But yeah, the answer is all the above.
All of this is well and good, but none of it really matters unless you have, like you mentioned earlier, a working out of the box solution. And so I can tell you firsthand how hard it is to just get an opportunity with a customer, let alone a top tier customer. And so the last thing that you want to do is get the business, provide a solution, they plug it in, and there's issues. So I I guess you really mentioned it all right there. It's the understanding of lessons learned. It's the reviewing of real life data, because simulations can only get us so far. Although they're a great guideline to point us in the right direction, we've got to get something tested and see some data to prove out the success. And so when we know where we are in real life, that helps us make the next step on the next generation of product.
Yeah, I think if anybody were to pick up one of our tech data sheets or, a data sheet on a specific product line, our focus really is out of the box solutions. It's not our company motto. Cutting edge technology is, but thanks to our world class global engineering team, their innovation and just their sheer expertise have allowed us to be and remain at the forefront of this industry. Our team really thrives on the challenge and consistently delivers on groundbreaking technologies. And it's really, really difficult, one, to get an out of the box solution, but it's even more difficult when you're targeting an application that there's really no way to validate or correlate yet. So, our team, our MPI team, has really done a good job at knowing how our products work in the real world.
So let me ask about the other side of the success of out-of-the-box solutions. So we've gone through the engineering and how we have to go through the design process and take all these factors into account, but the physical manufacturing of these products. So now we have 3 state-of-the-art facilities: Suzhou, Tijuana, and Dallas, where I am actually today. What would you say makes the manufacturing sites such a strength for production of these parts and coming out of the box working solutions?
All of these manufacturing sites, they're all equipped with the most current technology machining. We have highly skilled technicians that ensure the highest quality standards. Our facility in Suzhou, China caters to the APAC region, which is China, the rest of Asia, Taiwan, Malaysia, Singapore, Vietnam, Japan, South Korea. A lot of anything going into those regions will come from our Suzhou facility, but our Tijuana facility caters to North America, but also into some of those APAC non-mainland China regions also, with the addition of Irving, Dallas. That's been a real gold feather in our cap, right? I think the Irving facility has done the reliability stuff up until now, but we really look forward to getting the Irving operation fabricating the back end test, functional test components, and making that the gold standard for our North America manufacturing site. And just having manufacturing facilities around the globe just allows us to cater to our customers and provide quicker turnaround times and efficient distribution to our customer regions around the globe.
Can you tell us a little bit about how important it is to be local to the sites making the products that we are actually providing fixtures for, as well as the test houses that are performing these tests?
The great part of having local sales and field technical support near major semiconductor manufacturing sites is that customers can call on us at any time, and as they do, we can get there pretty quickly. As we're getting close to running out of time, I just want to summarize how we're able to deliver these out of the box solutions to our customers, and as why they're so critical as we move into the 224 gigabit PAM-4 realm. I know that's just another set of digits, but for us, it really is a generational leap to get there, and I think our customers are realizing it as well.
Yeah, it's a
So,
process. It's a process to get there, it's clear that we've got the experience and process in place to make the advancement, take the next step. So, as I said earlier, is it going to be easy? Not all the time. Is it going to be fun? Most of the time it is. So, I see it as a challenge, but one that's absolutely achievable. Awesome. Well, I do want to thank you for all of your commentary, your insights, your advice. We'll look at seeing you on the other side of 224.
all right,
All right.
thanks.
That's all for this week's episode of Smith's Interconnect 360 Connectivity Podcast. We hope you enjoyed it and learned something new. If you have any questions or feedback, please feel free to reach out to us through the form in our podcast webpage. Stay tuned for the next episodes in which we'll explore more topics related to connectivity solutions. Thank you for listening and have a great day.